Trigonometry is probably the most useful and beloved branch of mathematics. Unfortunately though, most students who learn trigonometry only learn how to use it. They don't get a good conceptual understanding of it. So what is trig about anyway? In this video, I want to show you the how and the why of trigonometry. This video is great for people who are just learning trig. This will help give you a good solid foundation, but also if you've already taken trig, my hope is that this video will help give you a good and better understanding of trig. We can study the etymology of the word trigonometry to get its most basic definition. The word trigonometry comes from two Greek roots. We have trigon, meaning triangle, and we have metron, meaning measure. So the most basic definition for trigonometry is the measure of triangles. Sometimes trigonometry is thought as the bridge that connects the more abstract maths like algebra to the more real-life sciences or maths like geometry. And this is important because before we want to cross a bridge in real life, we want to test it, we want to prove it to ourselves to make sure that it can support us. Similarly, we should test trigonometry to make sure that it works, and we should understand how it works before we actually try to apply it to real life. Now, trigonometry builds upon the foundations laid for us in Euclidean geometry, which is, roughly speaking, geometry on a flat surface. Now, the first thing we should remind ourselves of is that in a triangle, let's call it ABC here, based upon the side lengths of that triangle. In this triangle, all the interior angles, that is the angles inside of the closed shape here, this triangle, all those interior angles must add up to 180 degrees. Now, the other thing that is relatively new to trigonometry is that we will label these sides based upon what angle we are looking at. So in trigonometry, we will often choose an angle to examine. And let's say we choose this angle B here, the lowercase b. Now the opposite side from that lowercase b, this uppercase b side, we would call that the opposite side. And that's relatively easy because there's only one opposite side that is corresponding for a given angle inside of a triangle. But there are two adjacent sides, so we can't just call them both adjacent sides because we wouldn't know which one we are talking about. So instead, what we do is we call one the hypotenuse, and that is always the longest side in a right triangle. The hypotenuse will also be the opposite side from the hypotenuse. Then the other adjacent side to the angle we call the adjacent side. Sometimes you'll see abbreviations for these names like so. Additionally, we should be familiar with similar triangles. These are triangles that are scaled versions of each other, possibly oriented differently in space as well. Based upon this definition, all similar triangles will have identical angles and proportional side lengths. For an example, let's take two triangles here. One with side lengths A, B, and C, and the other with side lengths KA, KB, and KC, with K being the scaling factor. We can calculate the ratio of corresponding sides like so. We can divide A by B, and we can divide KA by KB. We can cancel out the scaling ratio K here to get that A divided by B does indeed equal A divided by B. For more on similar and congruent triangles, check out this great video here by Professor Dave Explains. Now, my last words of introduction will be directed towards my own personal terminology. Now, I use the word class to refer to all the triangles that are similar to each other. And I hope that this helps me explain the topic in a little better way, but this isn't a part of any official math repertoire or anything. Now, the angle-angle theorem tells us that if two triangles share two angles, then they must be similar. This is because the third angle in a triangle must always add up to 180 degrees. So if two triangles are to have a third angle that adds up to 180 degrees, then the third angle in those triangles must also be the same. Now, if we apply this to right triangles, we get something interesting, because a right triangle, by definition, has a right angle, aka a 90-degree angle. So if someone tells us another angle in a triangle, then now we have two angles in that right triangle, and we already know what class of right triangles this right triangle is in. For an example, if someone tells me that there is a 30-degree angle in a right triangle, then I now know that I am dealing with a 30, 60, 90 right triangle, which is a specific class of right triangles that we deal with a lot in trigonometry. We said previously that all similar triangles will have proportional side lengths. This means that in this 30, 60, 90 right triangle defined by the 30-degree angle, if we write down the side lengths, the ratio of the side lengths, then we will be able to use that for future 30, 60, 90 right triangles to our advantage. For an example, let's go ahead and write down this ratio of A divided by B, which in this case is the opposite side A from the 30-degree angle divided by the hypotenuse B. and we get that it is equal to 1/2. Now, let's take a new 30, 60, 90 right triangle. And let's say that we know that the opposite side, A, is equal to 2. How can we use what we had previously written down to figure out what the hypotenuse B is? Well, we know that A divided by B must be equal to 1/2. In this case, since A is 2, then B must equal to 4 for that fraction to be able to simplify to equal 1/2. So, we figured out that given one angle in a right triangle, if we had previously written down some ratio of different sides, then we could use that to figure out the other side. The next step is to actually create a trigonometric function that does this. The trigonometric function will take an angle in a right triangle, and it's going to spit out a specific ratio of sides for the right triangle. Remember, we can create a function that does this because given one angle in a right triangle, we already know what class of right triangle we're dealing with, and thus we can say that the ratio for all those different right triangles will be the same. Originally, these functions were defined off their tables called trigonometric tables. People write down all the different ratios for specific right triangles defined by their angles, and then they would use that to their advantage. The function that we've been dealing with specifically is called sine, and it's defined as the opposite over the hypotenuse. In this case, we figured out that sine of 30 equals 1/2. And you can imagine we could write down sine of all the different angles that are possible within a right triangle, and then we can use those ratios later for our advantage. The Greek mathematician Hipparchus is known as the father of trigonometry because he made the first trigonometric table, although his table was a table of chords and not sine. The two biggest cultures that contributed towards making the trigonometric tables for us today are the Indians and the Greeks. They made tables for such functions such as sine, cosine, tangent. We already saw that sine was defined as being the opposite over the hypotenuse. We defined cosine as being the adjacent over the hypotenuse, and tangent as being the opposite over the adjacent. Sometimes we use the mnemonic phrase SOHCAHTOA to help us remember this. The Greek mathematician Euclid, he standardized the notation that we use today, being sine of a theta, the angle, cosine of theta, the angle, and tangent of theta, the angle, with the angle being parentheses right next to the abbreviated function name. Sine and cosine are the two most important trigonometric functions. And right now we're going to expand the definition to be coordinates, x and y coordinates in a coordinate plane. So we have a coordinate plane here, and we've plotted a unit circle, that is a circle with a radius 1, on this coordinate plane. And remember, this is Cartesian coordinates we're dealing with. We can imagine putting a vector, and for our purposes a vector is basically a line segment. We can imagine putting a vector here on the circle, and with its initial point in the center of the circle and its terminal point on the circumference on the outside of the circle. And we can rotate this vector around the unit circle. And the convention that we use is that we start the rotation, a rotation of 0, at the right wing of the x-axis, and as the rotation increases, we're going to rotate this vector around, counterclockwise around the circle. So, we can imagine creating a right triangle from this vector. We already have the hypotenuse, which is the radius, and we're going to drop down the side from the terminal point of the vector down to the x-axis. That's going to be our opposite side of the angle. And then we have the adjacent side of the angle, which is going to be on the x-axis. So, we can calculate the sine and cosine of these angles. Sine of 30 is going to be the opposite over the hypotenuse, and then cosine will be the adjacent over the hypotenuse. And we can multiply both sides of both equations by hypotenuse to get that the opposite side, which in this case is the y component of the vector, the opposite side is equal to the hypotenuse times sine, and the adjacent side, which is the x component, is equal to the hypotenuse times cosine of 30. So we just figured out that given some vector, we can figure out what the x and y components of the vector are using sine and cosine and multiplying both sides by the hypotenuse. And this is something that's just going to be taking, you just need to do a lot of practice problems to really get this to be an intuitive thing. Because at first, kind of like, well, I thought this was triangles and not vectors. But whenever you take vector classes or physics classes, you can do a whole bunch of problems that involve using sine and cosine to figure out the x and y components. And so this is basically the intro to that, where you're going to be using right triangles from a vector, and the angle is going to be defining that vector, and then you're going to be using those trigonometric functions to figure out the x and y components. So far, we've defined our trigonometric functions based upon acute angles and right triangles, and then we expand that definition to be used for Cartesian coordinates, so we can use the trigonometric functions to help us figure out Cartesian coordinates from a vector. But the question is, how can we expand this definition for angles that are greater than 90 degrees? Because as you see here in this Wikipedia definition, the key word here is acute angle. We can only use this definition of trigonometric functions based upon right triangles, and right triangles can't have obtuse angles. So can we just not use trigonometry to help us figure out for vectors that are rotating more than 90 degrees? Well, actually, there is a geometric trick which we will do. So we're going to expand our geometric definition of the trigonometric functions using a bit of symmetry. So the way that we're going to do this is we're going to think of the vector rotated. So let's say it's rotated 150 degrees, and we're going to reflect it back into the first quadrant, because the first quadrant, that's the quadrant with angles that are less than 90 degrees, and that's really the only way we can think about angles being within a right triangle. So if we imagine a vector being 150 degrees and it's in the second quadrant, what do we know about that angle? Well, if we reflect that, we know that's 30 degrees from the other left wing of the x-axis. That's because the 180 degrees is a full line, and it rotates from one side of the x-axis to the other side of the x-axis. So if we imagine reflecting this rotating vector along the y-axis here, that will give us a vector with the same magnitude of the x and y components, but the y component will be the same and the x component will be the opposite. And we know that because all we did was reflect it. But now we've got this vector reflected along into the first quadrant, and we just knew that it's rotated 30 degrees from the x-axis, so we know what angle it is from the right wing of the x-axis over here. So we can essentially say that sine of 30 degrees is equal to sine of 150 degrees, because as you see here, both of them have the same y component. And similarly, we can calculate the x component, because the x components are the same distance away from the origin, for the x component, but they're in opposite directions, so they're going to be the negative of each other. So we can say that the cosine of 150 is equal to negative cosine of 30. And so essentially how we expand our definition of sine and cosine is we use this idea of symmetry to write down all the different values for these trigonometric functions for angles past 90 degrees. We can do similar exercises for angles that are in the third and fourth quadrants as well. So we can basically just use a geometric perspective and symmetry to help us figure out what values of sine and cosine for angles past 90 degrees will be. So that is the geometric definition of the trigonometric functions. We start with right triangles, and we create a lookup tables for these right triangles. Then we expand the definition of sine and cosine to apply for x and y coordinates in a Cartesian plane or Cartesian coordinate system, and we use cosine and sine to help us figure out the x and y coordinates of a vector. Then we expand the definition of those trigonometric functions even further by saying that we could use geometric symmetry and reflection to help us figure out values of sine and cosine for angles that are greater than 90 degrees. That is the geometric definition of those. There are other ways of calculating sine and cosine, which are the methods that computers use, and these are infinite series, using such methods such as the Taylor series or the Chordic algorithm. These algorithms are done using infinite geometric series, like I said, and they don't help give you a good conceptual understanding of how these functions actually work. So I didn't go over them in this video, but they still are very interesting and something that you should probably look into if you are interested in calculating sine and cosine for any computer science or something like that. Anyway, I hope that this video was beneficial to you and that you got a deeper understanding of these functions and how trigonometry actually works. Howdy y'all, I'm Nathan Cochran. I've always liked the idea of making math teaching YouTube videos and such like, but I've never done it before. This is my very first try, so it's been quite the hassle making all this video editing and teaching. It's the first time I've taught in this capacity either. Most of the time I'm making notes in Google Docs or stuff like that, so it's one of the first times I've ever recorded myself in front of a camera trying to teach a topic. So I've learned a lot, and at the beginning I was trying to go for perfection, but I quickly learned you can't be perfect on the first try. You just gotta learn from your mistakes, and as you continue on making more videos, you'll get better and better, and hopefully that will be the case for me. The reason I made this video right now is because one of my favorite YouTubers and teachers, 3Blue1Brown, that's his channel name, but his real name I believe is Grant Sanderson, he made this YouTube contest about making a math explanatory video. I first came across Grant Sanderson on Khan Academy, actually. I took his multivariable course a couple times actually, and I really liked it. Beautiful animations, soothing voice, and someone told me on Khan Academy told me about his YouTube channel. I checked it out, and boy, he has some great videos on there. He's a very good teacher, and his animations really make the teaching thorough and very understandable. I especially love his course, The Essence of Linear Algebra. If you ever want to learn linear algebra, you have to take that course, because I do not think I could have found a single textbook or video or any other teacher who could have done a better job explaining that course. He really gives a good conceptual understanding of how linear algebra works, and I really appreciate his effort and time that he spends into making his videos as good as they are. Anyway, I just wanted to tell you a little bit about myself, and I hope that you will hear more from me in the future. And I hope that as I continue to make more and more, that I'll get more subscribers and more of a following here, and hopefully I'll be able to be of a great help to many people. I always love teaching and helping others out, so hopefully I can be some assistance to you, especially as I get better. I'm not sure if I did very much good justice to the video I made today, but you know, you live, you learn. See you later.